Hey everybody, so in 8.1 we're going to be looking at arc length and surface area, hence the reason it falls into the Chapter 6 category and module for us this year. Similar to other concepts where if we increase the number of approximations, right, we get closer and closer to the actual arc length in this case, right? So if we increase those points along the curve, then the arc length of that curve will be more accurate. Similar idea once we move into the surface area. So our formula, once we have proven that, and if you would like the proof, it is in the textbook, or we can find it online as well. The formula for the arc length is, first of all, we have to assume that f prime exists and is continuous from a to b, and then it is therefore surface area equals the integral from a to b, the square root of 1 plus f prime squared dx. Okay. So again, you may use your calculator for these types of questions, so this is just simply a Math 9 type of question, filling in the information that you need to fill in. So in this case, we have s is equal to the integral 1 to 3 square root of 1 plus f prime squared dx. So simple side work is just simply going to be what is f prime. In this case, it's just a power rule, so we would have 1/4 x squared minus x to the negative second. Putting that into our calculators, I came up with an answer of 2.833. So that would stand for the distance along the curve f of x from 1 to 3. This next example, use a little caution, right? It's not just regular cosine here, it's a hyperbolic cosine. So a hyperbolic cosine, the derivative of it becomes y prime equals sine hx. I'll look into this a little bit more to find out how often something like this comes up. I'm going to guess that it will come up in the later chapters, which is why it's in Chapter 8, but we have not seen it up until this point. So just kind of bear with this for now, and we'll take a look more closely as we move through Chapters 7, 8, 9, etc. Okay. And another important thing to note, similar to our Pythagorean, right, we have cosine h squared x minus sine h squared x. That's equal to 1. So that's just a little bit of background knowledge that we do need to know about our hyperbolic trig. In this case, we're looking at a hyperbolic cosine. So we still set things up exactly the same way, right? We have our integral from 0 to 2. We have our square root of 1 plus sine hx squared dx. You can put this right into your calculator. At least on Desmos I was able to. I didn't investigate the 83s, 84s and find out the process for that, but I would assume that it's capable. But I did go through and do this one a little bit more by hand. So under the square root, we have 1 plus sine h squared of x, which means that we could replace that with, that's equivalent to cosine h squared of x. And then we can cancel out our square root and our squares and say that this is equivalent to cosine hx dx. And we know that the derivative of sine hx is cosine hx, so therefore the integral brings us back to our sine from 0 to 2, which would give us 3.63. But again, we could have taken this original Math 9 and had the same exact answer. Okay? And it's standing for this distance along the curve when a is 2. This example is telling you to use Simpson's rule. That's not a rule that we've learned yet, so I'm going to just do this one more example using the same exact method. Okay, we will get there, but it's not in this chapter. It won't be in this module, so we'll circle back later on. Okay. So I'm just setting this up the same way. I need my y prime, which is cos x. I have s is equal to the integral from 0 to pi of 1 plus cosine squared of x dx. In the calculator, gives us 3.82. Right, and Simpson's rule does give us the same idea, which is the 7.8 lesson. So we'll get there next chapter. One more concept in this section, similar, right, is now surface area. So if we know that distance along the curve, right, then we can think of this as if we do the circumference times that distance, that would give us our surface area. So down here at the bottom, you have your surface area formula. And it's going to be very, very similar to what we were seeing with our shell method, right? We have our circumference. So the 2 pi f of x is equal to 2 pi r, like it was. And that is your circumference. And if we take the circumference times the surface length, then we get our surface area. Okay. So this first example for this topic is calculate the surface area of a sphere of radius r. And that's all the information that they gave us. So we have to think about, well, how do we make a sphere? Okay. Well, if I have a semicircle with radius r, so that would be my equation. Let's write that down for you. Semicircle with radius r. That's what I'm creating. And I get this visual. That's a pretty crooked line. And now if I envision this rotating around the x-axis, right? Kind of like that jump rope example, right? If I had my jump rope perfectly as a semicircle and not more of an parabola shape, but it would create that sphere. Okay. So this is accomplishing what I need. We want to know the surface area of this. So we're going to need to know the arc length, and then we're going to need to know the circumference. So that means we need our derivative. Right? We have to prove this because we have r's in here, so we're going to have to do this completely by hand. So f prime is then equal to 1/2, using my chain rule, r squared minus x squared to the negative 1/2 times negative 2x, right? We're deriving with respect to x. If I rewrite this a little bit, I would have a negative x divided by square root r squared minus x squared. Okay, so from here, I kind of have the information that I need. So I'm going to go into my formula. Surface area, big S, is equal to 2 pi, right? From negative r to r would be from the left side to the right side. We need our f of x for the radius of the circumference. And then we're going to multiply it by the square root, the arc length of 1 plus the derivative squared dx. Okay, so now if we think about this, right, and we look to simplify, first of all, squaring that derivative is going to give us, let me see if I can write a little smaller to make this fit. It's going to give us an x squared over an r squared minus an x squared, right? The square root's gone, the negative is gone, dx. Okay. Now, inside of the square root is where I'm focusing. I want to combine those terms. I want to have a common denominator and see where that takes me. So I'm thinking of the 1 as r squared minus x squared over r squared minus x squared. And if I perform that addition inside of the square root, this then becomes 2 pi negative r to r radius r squared of r squared minus x squared times the square root of the arc length, which is now r squared minus x squared plus x squared is just r squared over that denominator, this. Right. Now I have a square root of a fraction, of a single term fraction. So I can square root the numerator and I can square root the denominator separately. So that means I have the square root of r squared, or just r, divided by the square root of r squared minus x squared. Well, that's great because I can cancel those two square roots out. So we've taken this all the way down to the integral of r. But the integral's with respect to x, so r is a constant, right? So we can just pull that out. So now we have 2 pi r, technically on the outside, integral from negative r to r dx. So if we integrate 1 dx, it returns to an x. So this is equivalent to 2 pi r x from negative r to positive r, which means we have 2 pi r times r minus negative r, or plus r. And finally, we get to 4 pi r squared. That would be your surface area of a sphere, which, not a coincidence, people. Okay, example 5. Now this is more straightforward, using the formula. So we need our derivative of our function, and we would then put the circumference times the arc length in there. So find the surface area obtained by rotating the graph of y equals x to the 1/2 minus 1/3 x to the 3/2 from 1 to 3, about the x-axis. So then surface area equals 2 pi integral 1 to 3 function square root of 1 plus, this derivative is 1/2 x to the negative 1/2 minus 1/2 x to the positive 1/2. dx. Into our calculator, Math 9 is 5.585. Okay. So this last page, quick summary, I'm just showing the two different formulas that we looked at today. Those are the big picture ideas from this section. These types of questions are typically very, very straightforward, so it's just a matter of knowing what the formula is. So conceptually, once you have your arc length, then the surface area, makes more sense, but make sure you have that arc length memorized.